Hi, we continue our discussions about different design examples for reinforced concrete pad footing. Based on a similar set of specifications, a pad footing can be subjected to various load cases. So far, we have covered two load cases. The first one, it will be only axial load. The second one, we have axial loads plus the moment in the major axis. Next, we're going to cover the pad footing subjected to axial load. Only now the moment is acting in the minor axis with the same magnitude of the moment but acting in different axes. You can make comparison in terms of the differences of the design calculations for these two examples. Without further ado, let us get started. These are the specifications. Assuming the exposure class equals to XT2, which is subjected to chloride attack and it is normally weight. The design life is 50 years. Concrete grade 30, unit weight of the concrete 25 kN per meter cube. Steel grade 500, soil bearing capacity 200 kN per meter square. Maximum aggregate size 20 mm. Column size 300 times 150 mm. Ultimate load equals to 1000 kN. No moment in the major axis, but we have 150 kN moment in the minor axis. The proposed bar size is 12 mm. First, we deal with the concrete cover. The calculation steps, it will be the same as the previous example, which for you to calculate the nominal cover, you need C mean plus the deviations. The deviations is 10 mm. C mean due to the bond will be equals to the bar size. As for C mean due to the durability, you may refer to table 4.4n. The concrete grade is C30. For the exposure class XT2, grade 30 concrete does not lead to the changes in terms of the structural class. 50 years design life is also not influencing the structural class. Therefore, we will maintain at the structural class of S4. For XT2, the C mean durability shall be equals to 40. Take the greater value of the 3. You have C mean equals to 40 plus 10 mm deviations. Your nominal cover shall be equals to 50 mm. Next, we need to estimate the size of the pad footing. Based on the prescriptive method, estimating the size of the pad footing shall be based on the service load. The questions only give us the ultimate load. Therefore, we will need to convert the ultimate load into service load. This is done by dividing the ultimate load with the assumed factor of safety as a compound of GK and QK of 1.4. The reason we use this 1.4 is we do not know the quantum of the GK and QK contributing to the ultimate load. Therefore, we are unable to remove the factor of safety of 1.35 from the GK and 1.5 from the QK. Considering their compound effect, we assume the equivalent factor of safety equals to 1.4. Dividing the 1000 kN load with 1.4, you get 714.3. Dividing 150 kN moment with 1.4, you get 107.1 kN acting in the minor axis. And then consider the self-weight of the peg footing, assuming it equals to 10% of the service load. Get the total axial load, which is 714.3 kN, plus 10% of this 714.3 kN, divided by the bearing capacity of the soil, which is 200 kN per meter square. We obtain an estimated area of the peg footing equals to 2.93. This gives us a guide that later when you need to propose the size of the peg footing, the total contact surface area to the soil should be greater than this 3.93. Having the contact surface area less than this is likely to fail in terms of the stability against the soil bearing capacity. Let us try this size for the peg footing: 2.2 meter, 2.4 meter, and 0.55 meter. Since we have the moment in the minor axis of the column, now the minor axis theoretically will have a longer width as far as the peg footing is concerned. Since we proposed the previous examples where we have the peg footing subjected to axial loads plus the moment in the major axis with the dimensions of 2.4, 2.2 and 0.55. Now for the moment in the minor axis, we're going to use the same size except now the 2.2 and 2.4 swap. The purpose is to demonstrate the differences in terms of the calculations later. Based on the proposed dimensions of the peg footing, multiplying these 2.2 meters and the 2.4 meter, you get your total contact surface area equals to 5.28. This area is greater than the estimated area. So, as far as soil bearing capacity, without considering the influence of the moment, it should theoretically be adequate. However, we are not sure at this moment, since we haven't considered the influence of the moment. Our next step it will be to confirm the soil pressure not exceeding the soil bearing capacity. You can use these equations to calculate the soil pressure. The axial loads, after removing the factor of safety of 1.4, the axial loads is equals to 714.3. We need the self-weight of the peg footing. This is calculated from the volume of the peg footing multiplied with the unit weight. The unit weight is given 25 kN per meter cube. The area represents the contact surface area due to the proposed size of the peg footing, which is equals to 5.28 meters square. And now the moment. Moment in the major axis is equals to 0, and in the minor axis equals to 107.1 kilonewton meter. You need the y and the I. These are geometrical property of the peg footing. The y represents the centroid of the rotation of the peg footing when subjected to the moment. By referring to the diagram here, you have moment in the minor axis. The centroid of the rotations, it will be here. Taking this as the reference point, the y here, it will be the half length of the width of the peg footing. The width is 2.4 meter. That means your y will be equals to 1.2. Since the major axis do not have any moment, that means this whole thing will be equals to 0 in the major axis. Therefore, you can choose not to calculate the y and the moment of inertia in the major axis. Even though you calculate them, later multiply with zero moment, the whole thing becomes zero. It will not influence the soil pressure in the major axis. Next is for you to determine the moment of inertia in the minor axis. You will need to be careful with the B and the H, since the formula to calculate the moment of inertia will differ in terms of the B and H. One of the width will have to be power of 3. Getting the B and the H confused in the formula would result in miscalculations in terms of the influence of the moment to the soil pressure. How do you determine the B and H? If you have gone through the previous videos of the previous examples, I believe you have no issue identifying the B and H that you use in the computations of the moment of inertia. Let's say now you are talking about the moment in the minor axis. The rotational axis, it will be here. The width of the peg footing in the directions of the moment rotations shall be the one to be power of 3, and the width of the peg footing not in the directions of the bending moment, it will be the one not to be power of 3. Therefore, based on the dimensions proposed, this 2.4 meters will need to be power of 3, and this 2.2 meters no need to be power of 3. The formula for the moment of inertia is BH power of 3 divided by 12. Then you get this. Now you have all the values calculated. Use the formula and you generate these results. Since you don't have any moment in the major axis, you will expect the stress it will be uniformly throughout the entire width of the major axis. There is moment in the minor axis. That means the soil pressure redistributes. One side will have higher degree of the soil pressure, while the other side will have smaller soil pressure. The calculated soil pressure will later be checked against the soil bearing capacity of 200 kN per meter square. Make sure the soil bearing capacity is not exceeded. In the case that the soil bearing capacity is exceeded, you will need to revise the dimensions proposed, and then recalculate again the soil pressure using this formula until you get your soil pressure less than the soil bearing capacity. Up to this stage, if you want to compare the calculation steps for the axial load plus the moment in the major axis and the axial loads plus the moment in the minor axis, both calculation steps it will be in common in terms of the applications of the prescriptive method. You are proposing the size of the peg footing based on the subversivity limit state. That's why both examples will have the service loads calculated using the ultimate load divided by factor of safety of 1.4. Another common principle it will be, normally we will propose a longer span of the peg footing in the directions of the moment. In this example, the moment in the minor axis, we will use a longer span in the minor axis. In our previous example, the moment is in the major axis, and therefore a longer span will go in the major axis. Next, the calculations of the soil pressure. Same formulas is used. That means in this example, the uniform stress it will be in the major axis, whereas the previous example, the uniform soil pressure will be in the minor axis, whereas in the previous example, the uniform soil pressure it will be in the minor axis. Because you have moment in the minor axis, for this example, you will have maximum soil pressure and the minimum soil pressure in the minor axis. And this is calculated on the basis of you correctly define the y and the b and h in the computations of the moment of inertia. The main difference it will be this. If you have difficulty identifying which to be power of 3, you can always sketch and determine the dimensions based on the directions of the moment rotations. From there, you are able to compute the maximum and the minimum soil pressure.